is about measuring H0 with lens quasars. That's all the tools you need to do this in practice. It's measurement. So that's how it works. If you have a quasar, so any light source that has variations, then what you will see, let's see if it works, yes, you will see the photons coming from each image, 2 or 4, usually coming at different times. And this time measures the ratio between these 3 distances. Okay, so in more detail, if you have so the delay from the photons to the source to the observer depends on the redshift of the lens, on this ratio of 3 distances. They are angular diameter distances, so H0 is in each of them, so they cancel out, and there is 1 over H0 in the end. This is the geometry of the system. That's the position of the source. You don't know it, but if you take relative time delays between lens images, this cancels out. And that's the problem, that's the lensing potential. So the photons are delayed because the light path to each image is different, but also because photons will probe the lens potential at different positions. So you have to know the lens model to convert this measurement into H0. Now, it's not a recent method, but it's single step. It's not a ladder, it's independent of anything else. No cepheids, no tip of the object, nothing like this.
So is this a photometric or a spectral?
So the time delay is, you can measure it in spectroscopy if you have a lot of telescope time, and otherwise you do it. And that's what we do. So we started this in 2004 with this program, CosmoGrail. And when we started to have delays, we teamed with Sherry Soulou, who invented this crazy acronym, H0 lenses in CosmoGrail wellspring. And now we went for a more simple acronym. So all the papers in the futures will be just time delay cosmography. And all the teams who do this have essentially joined. So, ingredients, you need time delays between the lens images. That's an HST image of one of the most beautiful lens on the sky. You need the mass in the unshiny ring, that's where the images sit. And you need the slope of the mass at the position of the lens images. Now we focus on these 2 things in this talk, but you also need to correct for any mass along the line of sight that leaks into the unshiny ring. So this is under control, whatever George said. This step is completely under control. And finally, all the analysis is blind. So you do all these steps, you never have any idea of any H0 from the beginning, measurement of the time delay to the modeling, correction of the line of sight. And if one day we find H0 equal 42, that's what we find in the papers. So time delay measurement. So this is the kind of data we have. Oh, there's a trend. Yeah. So the previous image with the HST, this is a ground-based image. So we deconvolve the data, measure the light curves from these blurred points you see there, and what gives us is this kind of curve. So I like to show this because this is really a cross-generation project. I like to tell my students that when they analyze data here, we started the project when they were at high school. Okay, so anyway, that's the type of curve we get. It takes a lot of time. Here is another object, observed with 2 different telescopes, 15 years between the 2 points here. And this is because you have microlensing by stars in the lensing galaxy that distort the curves relative to each other. And to compensate for this, these are very slow variations. So you need to observe for a long time to discriminate between the quasar variations and microlensing. Now, we do it faster. We don't do this for another 15 years. If we observe, this is not a zoom of this, it's new data. If you observe at high cadence, you start to see very small quasar variations that are at higher frequencies than microlensing. So if you want to measure time delays in less than 15 years, you can observe at very high cadence, once per day, very high sensitivity to noise, so you need a bigger telescope, so we have that. And there you see the time delays by eye. You see that's days. Time delays are of the order of days to weeks sometimes. So now, instead of 15 years, this is only 1 season. And you see now that you see very well the structures. We can measure the delays almost free of microlensing. That means sometimes. So it's half an hour per point on a 2-meter telescope. We did this for 3 years. These data are worth 30 minutes of a 2-meter telescope for every day for several semesters. And by the way, the data there is already better than what LSST will get, both in signal to noise and temporal sampling. But we have only one filter. So we had a lot of time on the VST parallel, 2,000 hours. That was a very large program from ISO. We got lots of gaps in the curve because of COVID. So I also tried to get time at La Palma, which is one of the rare COVID-free place in the world. And we observed this very particular object. Now La Palma has a volcano, so we decided to erupt during the light curve, so we still have gaps from time to time. But this is a very special object that is circumpolar, so we see it all the time. It has 6 images. So 1, 2, 3, 4 images of one object and 2 images of another object. So in this one, we get many time delays in one way. And that's the kind of curve you get. Again, time delays we see by eye. These two guys are really faint, so it will be harder, but there is hope to get to time delay as well there. So there are a few golden lenses like this, and we hope to get James Webb time on this one. Now, okay, we measure the delays, fine. We have published 7 so far, there is the 30 coming. But to turn them into H0, you need a mass model for the lens. The lens is here, and you have lensing constraint where the ring, the Einstein ring, sits. And this is the radial profile of the mass. That's where the Einstein ring is in the radial direction. And we do a test here because we are always playing for using 2 simple models. So we use, for example, power models for the mass and composite models, stars plus the NFW halos. And in fact, the 2 things converge to the same slope at the lensing, lensing constraints, and then, of course, to the same H0. If you do this, this is what we get for our 7 lenses for now, with a simple power law model for the lens, or a more complex one. H0 is essentially the same, it's on the high side. This is corrected for the line of sight. Now, lensing is known to be degenerate. There is one famous degeneracy called the mass shift transform, and this is this. If you have a source, you can kind of stretch or squeeze it, and then you change the slope of the mass profile in the lens plane, and you obtain the exact same observables, except the time delays. So if you use this to constrain your models, in fact, you're not sensitive to time delays. I show it in a different way here. So now this is where, this is a cut on the plane of the sky, and that's the different mass profiles for the lens. So we can make the lens sharper and add some mass, or make it shallower and subtract some constant mass. This will produce arrival time surfaces. That's the arrival time of photons as a position on the plane of the sky. Lens images form in potential waves, or wells, let's say, in this surface, because that's where the time is minimum. So the images for this split profile will always form at the same position. But the time delays, so the difference between this bump here and this bump in tau, is larger for the dotted line here than for the solid line. So you change the delays, but you don't change the other lensing observables. So now we include these in our models. So we take our composite models and include, sorry, I should have mentioned, so I lost all these technical issues. This is going through, in fact, one single parameter, lambda, that's change the shape of your lens. So we take the basic model, composite, and then allow for any possible change. So we include now the full degeneracy in the model. So of course, you do this, your error bars blow up, so you need to, for example, to get more data. One possibility to get dynamics of lens galaxies, but this is really a James Webb job, so it's very expensive. So we are doing it, but it's slow. Or you can go for dynamics of lenses that don't have time delay. So you don't get H0 from them, but you get the dynamics from these lenses, and you inform the lenses with the time delays of their shape properties. It's dangerous, but it's feasible because it assumes, so of course it's a hierarchical Bayesian analysis, it assumes that all your lenses with delays, the green ones here, and the green ones with no delays but with dynamics, are drawn from the same parent population, which is not obvious. I think on this we have to work a bit more. And of course there is another avenue, which is to use lens supernovae, but that's not the topic of the day. What we obtain if we do this, so if we do the hierarchical Bayesian analysis, if we assume that our composite models are not too simple, That's the values we get. That's the result I showed you before. Now you relate this lambda parameter, so you allow for the full degeneracy, full mathematically possible degeneracy. Then your error bars blow up, and you add information from the dynamics of lenses with no time delays, just the central velocity dispersion, and you assume that the lenses with time delays and without time delays share the same anisotropy. Then you get the same value for H0, but slightly bigger error bars. Now, if you assume that the lenses with no time delays also share the same radial mass profile, then you get a lower value of H0. But I think we are not done there because there are clear differences between the lenses we use with no time delays and the lenses we use with time delays. So now what we are doing to make sure that this point is here and not here, I think this one is right, it just has bigger error bars now. This point needs now a better sample of lenses with no time delays and good dynamics of lens. So my take on this is that don't trust too much this point at this point.
One sigma over.
Sorry?
These are one sigma.
Yeah. Yeah. Of course it's getting bigger, but it didn't change the mean value. Now I will show you another thing.
Okay.
You know dynamics of a lens, that's the one I showed at the beginning. That's an HST image of it. That's a fake image, and this Pac-Man thing is the mask we use to get, so it's an IFU spectrum. I skip the details of how we use this. We get the velocity dispersion field that we include in the analysis. So that's the dynamics of lenses with time delays. So we don't rely on any sub-sample, ancillary sample. If we do this for only one lens, that's what we get. So now you have this point, which is our H0 for 7 lenses and composite model. So not assuming the lambda degeneracy. This is now the one object I just showed you, also with a simple model. And that's what you get. Sorry. Yeah, this is now this lens, okay, if you include the 2D kinematics. So with just one lens, you get 9% estimate of H0, but it's one lens. We'll do another 30, hopefully with James Webb. Now, what's important here is that these points agree with this one. Now, even if you shrink the error bars, we are not drifting away from the value we had. So my take on this is, if you do proper kinematics of the lens and do more lenses with James Webb or Keck or ISO-BLT, it's very likely that we find high value for the lens. I don't care about being low or high. I want to be sure that the result is correct. Seeing that, it's very likely that we confirm our previous results. So that's the analysis we have. Now we can measure delays in 1 or 2 seasons. We can, so we'll have 30 more delays coming soon. We have only 7 lenses for now. In lambda CDM, simple composite model, no degeneracy, we find this value of H0. And now with resolved kinematics, we confirm this value, of course, with bigger error bars, because now we allow for full degeneracy. And for the hierarchical Bayesian analysis, combining 2 types of lenses, we're working on it. So that's my take. This is probably the result we'll find in the future. But again, we do everything blind and we publish what we have blind. So it may not do this. And then I just have a bonus slide because there was someone was showing before our plot with the dependence of H0 as a function of the lens redshift. Now we have this plot with these 2 guys with the lowest, so the highest H0 and the lowest lens galaxies that are right in the direction of the dipole. And all the rest on the equator is 70, 74, 71.
I think this plot appears to see in my paper from 2021, right? Which
Yes.
you acknowledged it.
So, yeah, okay.
It's a very cute result.
Actually, yeah. So the point is that, okay, this is part of a paper on something completely different, which is about explaining this by aberration due to the motion of the Earth compared to the CMB. So because you move towards a direction, the lens images you see are not where you think they are. And then you read in the lens potential at the wrong place, and then you may have an effect. And we don't explain this with the aberration.
Okay.
like a little bit of an outlier. This recent result, which is 64, 66. And all of those models, I guess there was a competition for them, right? And there seems to be, you know, if you're going to converge to 74.
So you mean in clusters or in galaxy scale?
If we're going to converge to 74, there was this science paper, right?
Yeah.
How do we see that as being impacted?
I would say,
is it the modeling, or what is it?
you know, if you could say our modeling is biased, then the cluster models are, two orders of magnitude worse. I wouldn't trust any cluster model for lensing cosmology, for time delay cosmography. If you're speaking of the supernovae that were
Supernovae.
yeah, but there are supernovae in clusters, or behind clusters, and supernovae behind isolated galaxies. The problem is that in the clusters, the models are really under constraint, and in single galaxies, there is they are discovered using ZTF. ZTF doesn't go deep, so you pick only the brightest supernovae, and this happens to be the one with delays that are almost zero. So they're not constrained in this one. So I think for now we don't have any lens supernovae that is useful for time delay cosmography. Of course, people put values of H0 and so on, but really the models. But in clusters, you already have a hard time to predict the position of lens images to what are cellular. So it means you read your lens plane at wrong place.
Anyway, you're going to have to explain that result, right? So somebody's going to have to sort of, maybe it's the clusters, maybe.
I think the future for lens supernovae is supernovae produced by isolated galaxies with very long time delays. But for this, you need to go deeper, and there you need the LSST. Because if you go deeper, you allow for lower magnification, therefore supernovae that are not perfectly aligned behind the lens and that have longer delays that you can measure. So if there is no delay, if you have a non-variable source, you don't do cosmography. You have a nice press release, but that's all.
Okay. Okay.
Okay, Wolf?
So, I don't know much about lensing, but is there a dependency on the redshift on this time delay? And do you know if, can you get, do people normally get the redshift of one of the sources, or the redshift doesn't really know?
No, you need to get the redshift of the lens and of the source, otherwise you can't do anything. And the dependence of the time delay on the lens depends on the lens redshift, not on the source redshift. The Einstein radius will depend on the source redshift, so it's there even in the first equation I showed. Now the dependence in terms of lens redshift, it works in 1 plus z lens.
So in the analysis of the mathematics of the loss dispersion map, how do you break mass, orbital, and isotropy degeneracy?
Sorry, I didn't get it.
How do you break mass, orbital, and isotropy degeneracy in the analytical models?
So there we are required. We use the SORON project. They have dynamics result kinematics of nearby galaxies with exquisite quality. So we use their prior on the anisotropy. And it's basically between minus 0.2 and 0.2. It's fairly loose prior.
If you are more generous with this prior, then how?
It doesn't change much actually. It's in the paper by Shajin Deta, this one. So we tried both. It doesn't bring much not to put the prior. It doesn't bring much to put the prior.
Yes, there's another possible effect. I guess this is not very symmetric, yes, potential.
Yeah, why?
Is it true that for this sample of lenses with preferential we pick, halos elongation Quasars?
I know, this is included in the analysis as well.
Okay.
Yeah, if it's so late or correlate, it's in there.
And you can see this kind of preference, yes, that they align with the right side.
So yeah, for now we have 7 lenses, but it's hard to tell, how the 3D potential projects and produce just 7 lenses. Which is why it's also important to increase the sample.
Okay, anybody else?
It's more a curiosity. How do you get so many time of observation on the, well, all telescopes?
Proposals are anonymous. So. No, I mean,
No, I mean,
no,
is
there
it
is
more
a pretty-
part of collaboration directly or
No, so the VST one was in fact because the VST was undersubscribed, so I applied for all the time and they did it. And the other thing is that I got an ERC, and in these ERCs you can apply for extra time, for extra money. Maybe I should not advertise that, but, and then you can, and then you buy your telescope time. So at the 2.2 meter at La Silla, it's just bought for 600,000 euros of time. Actually, each point of this curve is about 200 euros.
it's impressive.
Okay, now we know, it's an expensive field, so if there are no more questions, let's thank the speaker again.